So I was saying that it's going to be a kind of a bridge between antiferromagnetism and topological insulators, and more precisely Chern insulators. So a good background to build a Chern insulator is the Kagome lattice, which is, I guess, very well known for people here from the community of frustrated magnetism. Then I will go a little bit further into the details of what is a Chern insulator, what is a Chern number, the fact that it means that it has edge states and a Hall conductance. And then I will go more to the subject that these are things that were done a few years ago by other people. I will show you. And then we go further to what we have done for what is a cooling experiment for building an emergent Chern insulator. And another possibility is a switchable Chern insulator, what one could call a topological transistor. And at the end, give you some conclusional perspective. Excuse me 1 second. So, okay, the first part is based on very well-known work done since the year 2000 by Nagaosa's group, and there is also a nice paper by Claudine Lacroix, Benjamin Canal, Steifumier, and Dugaev and Bruno group about the interplay between a magnetic background and electrons hopping. Okay, so the problem is very simple. Imagine you have a magnetic background which is represented here by some kind of lattice and some big spins that you are going to consider fixed in the first time at least. And then you throw in electrons. So this green sphere with a small arrow represents an electron with a charge and a spin. And oh, great. Thank you, Grégoire. And well, the electrons hop. They hop from one side to the other, and they don't interact among them, the electrons. Let's start simple. But what they certainly do is that they interact. I mean, you have a Hund coupling between the spin of the electron and the pre-existing spin, which is represented by this vector n here. Okay. And since the Hund coupling has its origin in the Coulomb interaction, it's not surprising that this Hund coupling here would be much bigger in energy scale than the hopping amplitude here, which is tunneling between adjacent orbitals. Okay, this very simple model can be tracked in the limit. Again, I'm going to concentrate on the limit in which the Hund coupling is very big, and something you are welcome to do is you can make a rotation, a space-dependent rotation. The idea is let me go back. The idea is define the z-axis in the direction of the vectors for each side. So you do this with a unitary transformation is such that for each side n dot sigma becomes sigma z. That's the way you build the unitary transformation. And you define new creators and annihilators, or new spinor. This is a 2x2 component, the spinor of the electron. And if you do that, then of course the Hund coupling has become very easy because you have only the appearance of the z component of your spin. But of course the price to pay is that now your hopping amplitude has gotten this supplementary term here, which may complicate things. But the point is that if, as I said again, the Hund coupling is very big, so in first, when I say very big, is much bigger than these couplings here, in first approximation, you will have a huge separation of two bands, which are roughly, of course, the SZ spin of the electron is not a good quantum number because of this term here. But in first approximation, these two bands represent roughly spin up and down in the z direction, and then you get the low energy. If you are interested by the low energy physics or physics at energy much lower than J, then you just keep the lower band. And if you do this, you are basically doing what is called the adiabatic approximation. It's basically that you will forget about the spin degrees of freedoms of your electrons. And you will consider only that your electron has no more spins, but the spins is systematically parallel to the pre-existing magnetic moment on the site. Okay, this is a adiabatic approximation. And if you do this, then you say, okay, here the low energy degrees of freedom is spin up, so I'm going to consider that within this frame here, the spin of the electron is only up. I forget about the possibility of having spin down. This is a band which is far away in energy. And then basically from this, these are two spinors, but I'm going to reduce my two spinors to one spinor. And it's just a question of keeping only this term here. So I end up with a tight binding model in which, in the end, I don't have now electrons with spin, but electrons without spin. And I have a hopping term, which is going to be given by this term here. And of course, it contains the information of the pre-existing magnetic background. And if I do that, I will get basically a hopping term, which can be written like this, where theta E and theta I and theta J and phi I and phi J are the difference of angles between the adjacent spins, either azimuthal for theta or orbital angle for phi. And what you see is that now your hopping amplitude, it got a phase. So it's like having a kind of an emergent or an effective magnetic field, or gauge potential at least. And if you have a plaquette, you can try to compute the circulation of this gauge potential on the plaquette, and you may get a non-zero flux. And it turns out that this non-zero flux is going to be related, of course, to the configurations of your pre-existent spins. And this flux is going to be related to the triple product, or the chirality, the scalar chirality of your three spins. Okay? So the idea is that if you throw electrons in a magnetic background where there is scalar chirality, these electrons will feel somehow, because of the Hund coupling, a kind of effective magnetic field. Okay? That's the idea of the, which is not new. It comes back to Nagaosa's group. And so what is a good candidate to get chirality? A good candidate, as you know, a good candidate to get chirality is the Kagome lattice. So from the magnetic point of view, all what I'm going to say here is fully classical. So sorry if I disappoint you, but all what I'm going to say about spin systems on the Kagome lattice is completely classical. So, do you know this lattice? Have you ever seen this lattice? Okay, so this is the Kagome lattice with first, second, and third neighbors as they are drawn here. And of course, classically, we got recently very nice papers, among others by Grégoire, with Laurent Messieux, Claire Lullier, etc., etc. And in fact, we have borrowed the phase diagram from them for the ranging G2 and G3 positives. We are interested in G1, G2, and G3 positive. And in fact, the phase diagram already in this area here is quite interesting, with three different phases. A phase that is called Q equals 0, we'll come back to this one, and two kind of very exotic phases, non-collinear, non-coplanar phases, the Kubock dihedron 1 and 2.
Sorry, this is spin 1/2.
No, this is classical spins. This is fully classical, and it's going to remain like this till the end. And you have interesting lines. So this is the, I wouldn't say the ground state. I shouldn't say the ground state because it's classical. Let's say the lowest energy configuration of this Hamiltonian as a function of the values of the coupling for a classical spin model. Okay? And a particular interesting
no spirals in this somewhere?
Not here. Not, I don't know in other areas. You can ask the expert. And not here in any case. Okay. This point here, which we call highly frustrated point 1, is nothing else than the plain Kagome model, whose classical physics is already very interesting, with the phenomenon of order by disorder, selection of a coplanar configuration, so on and so forth. There is another point which is particularly interesting, and I'm going to do a small intermezzo in this point, although it's kind of out of subject of what I'm going to say later, but just because this is a community of frustrated magnetism, is this point here, what we call the highly frustrated point number 2, and it has recently been studied by Roderick Mosner group, and it's a very interesting point because it's even, wherever you know that it's happening here, well, it happens here worse somehow. It's even more frustrated, more liquid, if you wish. And I'm talking classically, of course, again. And for example, for the isotropic model, it's known to be a classical short-range spin liquid with no kind of selection of any kind, in contrast to what happened in the Kagome here, where you have selection of coplanar configuration. I advise you to read this very nice paper by Mosner group of last year about that. Well, we have investigated the same model in the presence of a magnetic field. And well, when you do that, it's still very interesting because it keeps being a short-range spin liquid, which has an important implication is that, okay, this model with a magnetic field on the z directions, you have broken the SO3 symmetry, but you still have the U1 or SO2 symmetry of rotation around the z-axis. So it's an XY model. But this is an XY model which we claim, we pretend that has no Kosterlitz-Thouless phase. It's short range everywhere till 0 temperature. This is known to happen on those lines here, but for a particular value of the magnetic field in which that appears what is called a pseudo-plateau. And in a pseudo-plateau, spin configurations are collinear. You can ask Grégoire why. He has a nice explanation on that. And only for a particular value of the magnetization or the magnetic field, the model here or also in this line would show a behavior without Kosterlitz-Thouless phase. But we'll claim that for this point, the Kosterlitz-Thouless phase goes away for the whole range of the magnetic field. Okay, so short range spin liquid, and by the way, with a mapping to which was used extensively recently by Ludovic Jobert and his collaborators, you can map this to a term with the mapping is the local rotation of the spins. I don't think it's worth entering into the details. You can map this to a model with some Jaroszynski-Mori interaction, and in fact, you can build a short-range spin liquid with, on top of that, spontaneous chirality. Okay?
Can I ask,
sure.
How spin correlations look like?
Short range, all of the, okay, good. For example, if you compute spin correlation here or all along this line, if you take a spin-spin correlation, it's going to be short range everywhere. But there are other operators which contains 3 spins, and those ones are going to be algebraic. You have algebraic correlation for some kind of yeah, well, more what is called the octupolar order of the spins. No, it's not quite the scalar chirality. But you can build an operator, although the spin operator has short-range correlations. You can build some operators, operators are classical quantities, if you wish, that do show algebraic decay. And you have a Kosterlitz-Thouless transition.
For them?
Yeah, absolutely.
So it's a local combination.
Absolutely, absolutely. You need 3 spins. And
Okay.
well, if you want to waste I can explain you, maybe as an appendix, I can explain you why the XY model on the Kagome does not show quasi-long range order for the spin operator, but, or if you wish, if you, in the XY, you know that, sorry?
Maybe collapse to a three-column model?
Yeah, okay. If you parameterize your XY spin by this, the Kagome, because of these 3 sides that you can permute, this will show short range order exponentially. But if you do this, well, let me put the 3 here. This one will show algebraic correlations, okay? And this is what basically would happen all along this line and also this line. But this point, we claim that there is no quantity like this that would show algebraic correlation, short-range correlation for everyone. Okay, this is a curiosity that is not quite related to what I'm going to say next, but just in passing like this. Okay, now I'm going to look, because if you remember the beginning, I was looking for chirality, and how to build chirality here. Well, there is one first way to get, yeah, sure.
So what do you mean by mapping to a chiral?
Okay, if you make local rotations of the spins, you have 3 sublattices in the Kagome. If you make different rotations for each sublattice on the Kagome model, you can pass from this model to a model like this, in which you have a Jalosinski-Mori interaction, and on top of that you put a magnetic field, and then you know that you will get a neat chirality, a non-zero neat chirality, but nevertheless having a completely disordered short-range model. This is what I mean by that.
Yeah, but under the mapping, so if I turn on my magnetic field in that H1, under this mapping, magnetic field will still be a uniform magnetic field, or it's going to be rotated?
No, the magnetic field stays a magnetic field. I can show you the details if you want about the mapping. Okay. Well, this is the only thing I wanted to say about this particular point from a purely classical magnetism point of view. And let me come back to my original problem, which I'm looking for chirality. You remember I was looking for chirality, and one easy way to get a spontaneous chirality is you locate comfortably here in the q equals 0. So now it's time maybe to show you, for the non-expert of course, what is the q equals 0 configuration. This is an example. So basically each sublattice has an orientation of the spins, and the spins point in the 120 degrees orientation, and then you repeat the same orientation for the same sublattice points. And okay, I need to define this on a Hamiltonian. Well, I have located here with first and second neighbors, but I can add third neighbors provided that I sit here. And I need to do that with an x-z interaction. That means that the x and y interactions are bigger than the z interaction. Delta, I need delta to be smaller than 1. Why? Because when I do that, well, at 0 magnetic field, you get the 120 degree star. And then when you put a magnetic field, so, but of course this star, as long as there is no magnetic field, no, even with a magnetic field, this star is going to be on the plane, because to favor the energy, you want the spins to be on the plane, and the x1 plane. And then you put the magnetic field on the z direction. When you do that, the spins are going to cant like this. This scenario is not going to happen if I would have taken delta equals 1 here. The case delta equals 1 was extensively studied by Mike Zitomirsky, for example, who is going to be around at some point. And there something different happened. That's why I need to put delta smaller than 1. When you put delta smaller than 1, your Mercedes-Benz star like this start to cant, and you get a configuration that is going to give you scalar chirality. So this is an example from a Monte Carlo done by Flavia, in which this is a cooling experiment in which you monitor the scalar chirality as a function of temperature for a given choice of the parameters, which I don't know exactly what they are, but it doesn't matter. And as you see, at some point, so this is an XY model, so you of course have no long-range order in the magnetic degrees of freedom, but still you may have a neat non-zero in the thermodynamic limit, spontaneous chirality, which remains so, and this is the appearance of the spontaneous chirality, which can have both signs. Okay?
You also have an easy transition?
So, okay, you have a Z2 breaking. Whether it's an easy transition or a first order transition, this I don't know yet. But
is it at larger temperature or smaller temperature?
Sorry, larger or smaller temperature than what? No, no, but this is the Z2 transition. This is the Z2 transition.
Okay, so related to the fact that spins can point in or out.
Basically, yes,
Okay.
absolutely, absolutely. So you see this. Sorry, you have the spins like this. You can them, okay. But then if you permute two of them, you change the sign of the scalar chirality. So it's either one way or the other. No, that's the Z2. Okay. Of course, that doesn't prevent that if you cool further down, you may get a costally towless transition to a quasi-long-range order of magnetic degrees of freedom. But at some point, I don't care about that. I care roughly about this transition. Okay. Well, if you do that and you remember, now imagine that you come back to the experiment in which you throw electrons on top of it, and the electrons will feel a kind of a flux. That's the flux pattern that they will feel. Okay. I stolen this picture from one of the papers of the Nagaosa's group.
Maybe a relevant question, but if that costless transition does occur, does it occur after this or below?
It would occur later. That's my feeling. Yeah, at a shorter temperature, a smaller temperature. It will occur. In fact, it will occur because the only point in which it wouldn't occur again is is this one. No? Oh, I went the wrong way. The only point where there wouldn't be a costally towless transition, so it would occur somewhere here. Okay. Okay, let me continue. There is another way, a more exotic way to get a spontaneous chirality. Is now you locate here in the Kubock-2 phase. So you need the couplings, second and third neighbor couplings to be in this area. You put a magnetic field, and you put a Jałodziński-Morier interaction, which is okay, there is a convention problem here. You put a Jałodziński-Morier interaction which is alternated for up and down spins. We can discuss maybe later if you want what is the idea of putting different kind of Jałodziński-Morier interaction. But imagine that you put a Jałodziński-Morier interaction, which is the D vector is pointing in the Z direction, but with alternated value for the D on the up and down triangles. Well, if you do so, and you do the same kind of Kulik experiment, you will again get a spontaneous chirality, but with a much more exotic pattern. Now you will have either the down triangles that get a positive chirality, or the up triangles that get a negative chirality. This is a snapshot, or how the triangles, of how the spins would look. So you see, here in these triangles, the spins do have chirality, while in the adjacent triangles here, they are parallel. Of course, they don't show chirality. Okay.
Sorry, but why do you need Jałodziński-Morier? The Kubock is already non-planar.
Yeah, but you don't get a neat. Okay, good. You get okay. In the Kubock, you would get this, or the opposite, minus and plus. But the neat chirality would be 0. Here you get the neat chirality. That's why we need to put the Jałodziński-Morier. And so this is again kind of cooling experiment. So as you see here, this is a cooling experiment in which we monitor the chirality of the up and down triangles for many shots, if you wish. So as you see, the down triangles can only have positive, either 0 or positive chirality, and the the up triangles either negative or 0 chirality. And of course, when one has 0, the other has a non-zero, and vice versa. And again, this is the plot of the neat chirality as a function of the temperature. Is the equivalent of the plot I showed you before. I agree that is a more exotic scenario, but just in case you didn't like the first way of producing a spontaneous chiral magnetic state. Okay, so yeah.
A technical question for one slide back.
Sure.
So I do remember when you introduced the Jałodziński-Morier, it's a question of certain conventions of how you go, whether you go along the
Okay. Okay.
So
For me.
Just let me ask this question. So your statement about staggered Jałodziński-Morier can be gauged out by essentially saying I have a different going around my lattice.
But it's not a question of pre-explication. It changed the physics. In fact, I'm going to use the two kind of Jaroszewski. When I'm going to build my topological transistor, I'm going to use the other kind of Jaroszewski-Morilla. But it cannot be gauged out. I mean, it's really, these are two physical different configurations.
They're different, but you can just declare a different path, how you go, and then it will be uniform.
I'm not assuming that I can tune it. It's either there or not there. I don't know if I answer your question like this. Sorry if I wasn't clear. So I'm going to consider the two possibilities, but not that I can tune them. Okay? Okay. Well, okay. Now let us go back to our electrons. So we're going to throw the electrons on this background. And well, the first thing you can do, for example, is that you can do that in a perfect clean translation invariance configuration like this one. Imagine you take the Q equals 0 configuration with some neat chirality. You throw the electrons here and you try to solve the problem with the flux. Well, you can do that. You have translation invariance. You can Fourier transform, and you can work with the block wave functions, and you can use then all the machinery of the topological insulators that is well known. And in particular, okay, there are three quantities that you can compute to diagnose a Chern insulator. The first is the Hall conductance, which is here. And this Hall conductance is constructed with what is called the Berry connection. And the Berry connection is basically the sandwich between one block state as a given k and the derivative of this block state and this of this same block state. And this expression built in terms of the Berry connection, thanks to Stokes' theorem, can be recast as a function of what is called the Berry curvature, which is given here. Again, these are my, sorry for the change of notation, I'm sorry. These are again my block functions. And in fact, when you have a completely filled band and then a gap, then you have an insulator, of course. And if you make this computation on the entire Brillouin zone of your filled band, then this is a topological invariant, which is called the Chern number. And in fact, it is an integer, which is called the Chern number. And the Hall conductance is going to be given by the product of E squared over H times the Chern number, which is going to be an integer. People expert in solid state physics and have worked on polarization of charge and all that, then they know that there is another way working with the polarization operator to relate the Chern number to the presence of H states. Wherever you have a non-zero Chern number, then if you have a sample in which you have H, you will certainly have H going around. So let me show you an example. We have taken the configuration, the Q equals 0 configuration on the Kagome model on a finite size. And then it's a question of diagonalizing the free electron Hamiltonian on this finite piece. So what we take is we take a strip which we make periodic in one direction. So momentum is still a well-defined number in this direction. But then we can either choose to also make it periodic in the other direction to make a torus, or leave it open. Of course, if you leave it open, then momentum is not a good quantum number in this other direction. So we can only plot the spectrum as a function of the only good quantum number in both cases, which is kx. And what we get is this. This is for the torus. This is for the cylinder, for the open strip. Do you see the difference? So here you see a clear insulator. So you have six bands. These are the three that I told you about, the lowest energy Hund coupling. These are the three high energy. Okay, so you have 6 bands in total, and the difference you can see between this and these are this presence of states that are present in the case where the system has an edge and not where the system has no edge. So these are edge states. Okay?
So that's for
Go ahead.
These are spinless electrons.
No, these are, now they have spin. They have spin. Okay, these are,
You project, I mean, in the very beginning you do.
yeah, sorry, let me explain it again. I throw electrons in a magnetic background. If the Hund coupling is very big, the low energy physics is the spin of the electron pointing in the direction of the spin. These are these three bands here. You still have three bands because you have three sublattices. But of course, there are the high energy degrees of freedoms, which is the spin pointing in the wrong direction, if you wish. And these are these three bands here, which I won't care.
you diagonalize the full Hamiltonian.
Yeah.
What's the value of J?
Sorry?
What's the value of Hund's coupling here?
I can't tell you. I don't. It was order of 5, something like that. Compared, J over T was order of 5. If you put it much bigger, you will roughly open much more this gap here.
Can you assign chain number to each of these bands?
Sorry?
Can you assign chain number to each?
Yeah, of course you can compute, and it's going to be 1, 0, minus 1. Okay? You can, yeah, of course you can compute the Chern number.
Number for the upper three bands are also non-zero?
Yeah, absolutely. Then you start the other way around. Absolutely. And you can do that as long as you have translation invariance. And if you have translation invariance, then you can build those states here. Oh, sorry, no, I went in the wrong direction again. Sorry, I'm sorry. You can build those states, and you build the Berry connection, Berry curvature. You compute this integral, you compute it numerically, and you get a Chern number. But what happened if now, yeah?
So this is calculated in the Z2 symmetry broken phase, where you have one chiral.
Yeah. In a chiral, in the presence of a chiral background, absolutely.
And for the purpose of this calculation, the XY component is also taken to be ordered. Is that correct?
Yeah, because it's a finite size basically, no? So it.
There is no costless Alice physics.
Yeah. Yeah, I mean, our feeling for the moment is that it doesn't matter. Maybe it will matter in some more subtle way, but for the moment, our feeling is that what is happening in the XY, I mean, the precise magnetic order, local magnetic order doesn't matter much. That's our feeling for the moment. What is important is that you have in the thermodynamic limit a chirality.
So you have chosen the background magnetic order, right?
Yeah, okay. This background here is the perfect Q equals 0. It was put by hand.
Yeah, okay.
It's not the product of a Monte Carlo. We are going to that. It was put by hand, so we have translation. Okay, no, this one here is just numerical computation, but put by hand. But what I say here, if you want to compute the Chern number, sorry again, like this is assuming that you have translation invariance, and for this, you need to put by hand a clean Q equals 0 configuration.
So there's no magnetic fluctuation.
We are going to that. We are going to that, okay? So that's the... Okay, what happened now if you put the snapshot of the outcome of Monte Carlo? Then you don't have translation invariance anymore. So you can forget about using the block wave functions, computing the Berry connection, the Berry curvature, and all that. And what remains is a numerical computation of the Hall conductance. This you can still do. And in fact, of course, we were not the first in having this idea. Of course, this was already suggested by Nagas, and then it was also obtained by the group of Claudine Lacroix, Taifumi, etc. And in fact, okay, this is a numerical computation. So you move the Fermi energy. Okay, what you do? We do a Monte Carlo, puff, and you cool down, and you stop. And now you compute numerically the Hall conductance as a function of the Fermi energy. And you get this for a Hund coupling of 4, taken T as 1, and 0. As you can see, if you put Hund coupling 0, nothing happens. Absolutely nothing happens. But you get, of course, when you get a non-integer Hall conductance, is that you are not in, it's not an insulator, you're in the middle of a band. To have an integer Hall conductance, you need a completely filled band. So this is what happens here. This figure, we produce this figure, but this figure you can find the very, very same in this paper by Taifumi et al. Of 2006. And this is when you cool down at temperatures which are 10 times smaller than the relevant energy scales for the magnetic degrees of freedom. I mean, the system is really very well ordered. It's although it's a product of a Monte Carlo, it came out from is almost like a perfectly made by hand configuration. Yeah.
And so when you do the simulation, your magnetic order you simulate in finite cluster.
Yeah, this is in a finite
So,
size.
and so at the boundary, you don't probably presume you don't have Q equals 0 order, right?
Yeah.
There is some
Well,
kind of
well, then
border.
you can compute the whole conductance without border. I mean, that you know that if you open a border, you will have these edge states, but you can, in principle, compute the whole conductance without border. No? I don't know if I answer your question, but if you put borders, yeah, something in the boundaries strange will happen. Yeah.
So these are numerics without edges.
Yeah.
So what I'm asking, so the flux comes from spins.
Yeah.
Okay, in that case, Q equals 0.
Yeah. Absolutely.
Near the boundary, if it's open boundary for spins as well.
Mm-hmm.
Like
Yeah. Yeah.
That there can be reconstruction of magnetic order.
Yeah.
Such that near the edge, the flux can be
Yeah. You mean that the spin configuration near the boundary will be distorted? Yeah. Yeah. Sure. But I mean, when you have an insulator, this won't matter because of the rigidity precisely of the Chern insulators.
Yes. So I understand that you still have edge
Mm-hmm.
current.
No, on the boundary. I mean, the fact. I mean, if you are well within a gap, and you have a non-zero Chern number, in principle, a small distortion of what is going on the boundary shouldn't change. You cannot go abruptly from 1 to 0. I mean, if you have a Chern number 1, it will remain so until you close the gap and you reopen it again. So the idea is that it's true when you have boundaries, what is happening with the pre-existing spins on the boundary will be distorted, but still this shouldn't matter. Okay, that is a good point. Okay. But do you remember that the idea was to make cooling experiments? And you don't know, in fact, depending on the value of the neat chirality, you will get, if you are interested in the first band, you will get either a Chern number of 1 or -1, depending on how the chirality went. Well, let me convince you about that. Well, first, before that, now what happens if I cool down my spins, but I stop not at very, very low temperatures, but I remain at temperature slightly below the critical temperature, but not that low. And then I compute for the electrons the Hall conductance, something important for the moment. The Hall conductance for the electrons is taken at t equals 0. Of course, later on I will show you what happens if you put temperature in the electrons, but then you have to fix the problem of energy scales of the electrons and the spin degrees of freedom. For the moment, I'm going to show you the figure of, so we take the spin configuration, we make a Monte Carlo on the spins, we cool it down until slightly below the critical temperature, and then compute the Hall conductance. And you get something like this for different values of the temperature. So here is again the t going to 0 limit is the same figure that I showed you before, and you get here different values of the Hall conductance. Of course, what is happening is that the gaps are not very well formed, so the Hall conductance is not quantized until you really reach very, very low temperatures. No? And to convince you that is what I decided to name a spontaneous Chern insulator is that you repeat the experiment. You make the experiment one time, you get the chirality plus, but you do it another time and you get it minus. And of course, this changes the sign of the Hall conductance. And in the end, you can get, both both sides. These are different cooling experiments, different seeds, and you see that you can reproduce the same curve, but one way or the other. Okay, so do you have questions so far?
Sorry, so the spins are simulated in classical way,
Yeah.
the classical configuration, but then what formula did you use to calculate the chain number then? Because actually for arbitrary spin configuration, you do not have transmission invariance.
We don't compute Chern number, we just compute the Hall conductance. That's the only thing we are. Sorry?
So how do you calculate the Hall conductance?
With the Kubo formula.
Kubo formula.
Of course, we cannot.
It's like somewhere you take the whole cluster to be periodic.
Yeah.
Then you need to repeat.
Yeah. And you use the Kubo formula for the electron problem. Okay. Another idea that I wanted to share with you is that let us go back to our classical spin model. And we can focus in all this area, which is the Q equals 0 area, the same as before. But now we take a Jaroszynski-Moria term which has both sign, which have the same sign for both triangles. So, and we put on top of that a magnetic field. So if you do that, this is known since a long time. Again, I think Claudine Lacroix, but also Mike Zitomirski had intensively work, also Claire now at some point, work on that. If you do that, so Jaroszynski-Moria, same sign for both triangle, and magnetic field. If you do that, you will get a scalar chirality, but now whose sign is not going to appear spontaneously. The sign is going to depend on the magnetic field, on the sign of the magnetic field. So if you put positive magnetic field, you will get one sign of the chirality. You put negative magnetic field, you will get the other sign of the chirality. And well, that means that now if you again throw electrons on that and you cool down, and then something you can tune is the magnetic field, with like having a Chern insulator in which by tuning the magnetic field you can switch from Chern number 1 to Chern number -1. That means that, for example, if you have an eraser, let me know. Well, if you have a sample which is, oops, I don't want to break. Well, you have a sample which is like this. So for C equals 1, you would have here electron. Oh, thank you. Merci, Greva. So imagine you have a very big sample. I don't even want to see where is the edge on this side. And if you have C equals 1, you would have electrons circulating on that direction, but they cannot circulate in the other direction. Whether if you have C equals -1, it would be the other way around. And now you can tune this with a magnetic field, which is very easy to tune. Of course, you have to cool down enough, but you can tune that. So that's the project of a switchable Chern insulator with a magnetic field. Okay, and that's it. Let me make a recap of first of what I say is first on the Kagome magnetic model itself. So we see that there are different ways of building a configuration in which a spontaneous chirality, neat chirality, not alternated chirality like in the QBOC, but neat chirality appears with a spontaneous symmetry breaker, and you can have either positive or negative chirality. This many couplings Kagome model is very interesting for those who are interested in generating short-range classical spin liquid. And it works to produce either spontaneous or tunable, spontaneous Chern insulators or tunable Chern insulators, what I call topological transistors. As perspective, I would say, well, all the computations of the Hall conductance I have shown you were done at 0 temperature. You can play the game of putting temperature in the electron, but then you have to decide about the energy scales of the electrons compared to the one of the spin degrees of freedom. No? And of course, it depends on the material. But in principle, you can do it. You can even do better, and this is a procedure that has done by many nice works by a Japanese group working on skyrmion, is that you can play the game of making the feedback of the electrons to the spins. I mean, you throw the electrons, you diagonalize the Hamiltonian, you see what happens. You compute, for example, the spin expectation value of the electrons, and you put back this now as a supplementary local magnetic field to your spins. You keep on your Monte Carlo, you stop the Monte Carlo, re-diagonalize the electrons, you see what happens with the local magnetic field, so on and so forth. And play with the different time scales for the feedback between the magnetic background and the electron. And of course, what if you can do that also for quantum spin systems, in which you would have a chiral spin liquid coupled to two electrons like this. And I thank you very much for your attention.
More questions?
Yeah.
So if you say about the chiral spin liquid, so would that be matter at all that there's like topological feature in this chiral spin liquid, or is it just about?
Yes, it's topology against topology, because indeed, the classical background here has nothing topological there. Yeah, I mean, basically you would, here I'm dreaming, it's wishful thinking for the time being, but you would have edge excitations with magnetic or charge degrees of freedom, for example. Could be quite kind of fun.
I guess you can dream even out there, like you can dream of realizing a chiral spin liquid starting from your classical spin, right?
Yeah.
Because if now your Chern insulator is not like well, if it's like in a not insulating state, then you can have like a chiral spin liquid out of the electron out of the spin.
Yeah, you're right. Out of the spin of the electron, you are right. Yeah, yeah. If you go down again with a Hund coupling, yeah, indeed, yeah, and you get back to life the spin of the electron. Yeah, indeed, yeah. You can play quite a lot. Yeah, indeed. But it's going to be tough. It's going to be tough. Yeah.
But also, as a remark, so if you assume that your spins are not completely classical, large but finite, right? You have magnets.
Mm-hmm. Yeah.
And those actually give current.
Well, you are perfectly right. Yeah, yeah, yeah. There is a whole. Yeah, absolutely. You are perfectly right. In fact, this I should have say that. Thank you for this remark. Indeed, you have these chiral magnons in which this Kagome model is a very good laboratory precisely for that. Indeed, indeed, yeah, absolutely.
In fact, if you continue this line, for the chiral magnon mode, the situation can be made much simpler and much more realizable. In fact, some of the systems do exist already. And it's ferromagnet, which is much easier to manipulate with the Chern schematic.
Yeah.
And that gives the Chern number to the magnon band. That's
Indeed,
that's
indeed.
realized already.
Indeed, you're right. Yeah.
And actually, maybe it's a tangential thing that now, if you're thinking of looking at such a system, then the question is, okay, now you have a ferromagnet. So how if you keep your Kunz coupling only with electrons are not going to feel any Berry space. But when you have the Zaleshinsky Marie term, it implies spin orbit for electrons as well. So if you start modifying that coupling term of electrons to spins in a similar manner, you may acquire.
That may be another origin for this mechanism. Yeah, yeah, yeah. Why not? You're right.
Because you mentioned tangentially the skyrmions, friends and spintronics do work hard on making your dreams come true, and that's the basic sort of the building blocks ferromagnets with some weird interaction.
But I cannot talk about ferromagnets in the highly frustrated magnetism conference. No, I cannot. Grégoire would be very angry with me. But you're right. Yeah, it's true.
about your curve where you show the whole conductors as a function of the temperature of the spins, but for different temperatures, if I understood.
Like this one.
Yes.
There's one which looks really ugly, no? This very low temperature here. This one looks ugly. Don't know why.
So does it happen sometimes that the spins are still quite disordered, and nevertheless you get almost quantized whole conductance? Or
We would like to investigate this. You see here in the blue curve, no, for this temperature, you start to get almost quantized. So you start to kind of open the gaps.
So we don't see where we really don't really know what the spin configuration or order it is.
No. One should show a snapshot. Yeah. And also the spectrum of the electrons to see the band structure somehow. No, also.
The transition you showed, you made some comments about it, but I didn't catch it. So is it a well-defined Ising transition? Do you really see Ising criticality?
No. Okay. Oh, sorry. I don't know what I did. Okay. You're talking about this transition. This one, for example.
Yes.
I don't know. For example, on the Kubok, I think Philippe Zanzingre worked quite a lot. And in the Kubok, you have a transition. You don't have a neat chirality, but you have an alternated chirality like this. And maybe you also. But in any case, I know Philippe Zanzingre tried to work on identify this transition, and it seems that it's first order. Here it's a bit early. I'm interested in knowing what kind of transition is going to be, but it's a bit early to say that.
So there's a XY order as well, right?
Sorry?
I mean, there's an XY order.
I mean, you expect to have a Kosterlitz-Thouless transition to a quasi-long-range order somewhere here, no? But this is a discrete symmetry breaking. This one I'm showing here.
For sure, but actually, are you sure they cannot happen at the same time?
No, I'm not sure. I mean, I don't think they will happen, but I have no proof or argument for. I think they won't happen either, because for example, on the Kubok, it doesn't happen at the same temperature. Sorry. Okay, if you locate here, you have a similar transition. You locate here, but without a magnetic field. You take this model and you locate, for example, here. And this is a transition that has been studied by Philippe Zanzingre 15 years ago. And so you don't have a neat chirality, but you have an alternated chirality, staggered chirality. And that's what I'm saying. The transition do not occur at the same temperature than the Kosterlitz-Thouless transition.
Sure, they don't have to.
They don't have. They could.
Yeah, so when that happens, it's probably a first order, right? You have like two other parameters at the same point.
Yeah.
That would be highly fine-tuned.
No, first order is
I mean.
Multi-critical point is fine-tuned, right?
Yeah. But.
They would occur at very different depth of scale. So you need a.
Why? They're all the same. There's only one and you scale with J here. Those transitions should be controlled by the same scale J.
So it's a delta and a J. Yes.
Well, I don't know. Yeah, I don't know how.
Yeah, how small that
Oh, the delta here, I have to put it because if I put the isotropic model, something different happens. I mean, because of order by disorder, you get a selection which is coplanar, and then everything goes down. And I have to put this delta to get chirality. So to answer your question, there is nothing that forbids the two transitions to come at the same time, but I think there is nothing neither that force the two transitions to come at the same temperature. And in fact, in the Kubok, they don't. Okay. And sorry, thank you for the organizers, two of them, for the invitation to this very nice workshop.